chord. So there's this Fano's inequality that says that if you look at this Bayesian hypothesis testing problem, there is this lower bound. There's this lower bound in terms of the mutual information of Z and J, and this log of the number of hypotheses over which you're trying to control the error. And so the mutual information is defined as the KL divergence of the full distribution of Z and J, or the joint distribution, with respect to the distribution that has independent marginals matching the marginals of the joint distribution. Okay, so this is a product distribution. This is a distribution whose coordinates are independent when you draw from it. And the distribution for this, the first coordinate, or the Z coordinate, is just the marginal distribution of Z under this, and the distribution for J is the marginal distribution of J under that joint distribution. There are some alternative expressions. So there are many alternative expressions for the mutual information. One is this average that we discussed last time. So 1 over m. So this is basically an average of the KL divergence of p theta j's to the marginal distribution of qz. You can think of this marginal distribution. You can also write it as q bar if you want. It's just the average qz, which we also represent as q bar, is the average sum j from 1 to m p theta j. Okay, so this is a mixture distribution, which is mixing all these distributions with equal probability. Okay, this is the natural marginal, because j is uniformly distributed. Okay, so that's the result, whether we have time to prove it or not. But if you consult any information theory book, gives you this proof. So the idea was to, so is this sort of clear? So the idea was to try to, so our lower, so Minimax lower bound, or Minimax error, let's say Minimax risk, would be lower bounded in our case by delta squared times this probability. So it's going to be bounded by something like that, plus log 2, and then divided by log m. So if I try, for example, to make this less than 1/2, then this would be bigger than delta squared over 2. Okay, so delta squared would be my, up to constants, my lower bound on the Minimax risk. A simple way to, in order to bound, so the m is the cardinality of the packing that you construct. In order to bound this, we can have different upper bounds, further upper bounds. One upper bound is that the KL divergence is sort of convex in the second argument. So if you expand this, you get an inequality. So basically, dp theta j relative to q bar, this is lower bound, upper bounded by 1 over m p theta j prime, j prime from 1 to m. And so if you plug back into this equation, you get this further upper bound, which is further upper bounded by the maximum of these quantities over all possible distinct choices of j and j prime. So you can think of this as the diameter of this set in the KL divergence. Okay, so if we call this, let's say d, I could further bound this by basically the Minimax lower bound would be delta squared. The bound is going to be, so this is going to get smaller if I replace it with a bigger number. So I get a better, like another lower bound. So d plus log 2 divided by log m. usually this log 2 can be ignored. It's just gets absorbed into the D. So the thing is, like, I have to sort of control the relation of D and log M. So you want a packing such that, so if you make delta small, sorry, yeah. It doesn't matter, actually, if you're not going to choose 1/2. So that your book does it, but it's just any constant, as long as it's any constant less than 1. It could be like 0.9, right? It's just for convenience. And you'll see we'll not gonna stick to that. So if it's like 0.9, what I would get here is like less than 0.9. This is going to be bigger than 0.1. So as long as we get a strictly positive number here, that would work. We don't care about like leading constants, so that would do. So we have to like balance the two out. And as I mentioned, there is some tension here when you try to. So you want to find a packing. So you fix the delta. Let's say you find a packing. You want it to be large. And so there are two ways to make this small, like increase the size of the packing, decrease the diameter in the KL. So what you want to have is like a set whose diameter in the KL is small enough, but at the same time you can pack a lot of things inside. So if you can pack a lot of points in the row metric in a subset of theta, while the diameter in the KL remains controlled, then this would work out. So the easiest way to see is like to see some examples. The intuitive idea is that you want these to be indistinguishable. So the diameter being small means these probabilities are indistinguishable, but the corresponding parameters are delta apart. So that what makes it work. It's like that strategy is sort of clear. So let's see some examples. You'll see how this works out. So consider the simplest case like the normal means model. Here we have y is distributed like theta sigma squared in, right? So that's saying basically I have y1, y2 up to yn. This is theta 1 up to theta n plus noise, right? W1 up to W. And so the different thetas could be potentially different. And the noise is, these WIs are IID normal 0, 1. So for some theta, which belongs to this capital theta, which is a subset of Rn. So first, let's say there is no restriction on theta. So let's see how well we can do. So what is the minimax lower bound of this? So let's try to do a naive bound first. So Rn is sort of unbounded set. I'm gonna like pick any subset in there. If I pick a subset in there, I get the lower bound of the minimax. So I'm gonna like do for E2. It's the unit ball of L2. E2 is the unit ball, so this is the ball of radius 4. L2 ball of radius 4. We'll get 2 packing inside this, okay, of size m. Then by a volume ratio argument, if you recall, basically if you compare the volume of 4, this is the volume of this, is 4 to the n times a constant, which is the volume of the unit ball. It's just so let's say volume of 4 E2 divided by roughly, this is how many I want a 2 packing. So Is this really? So let's go back to what I'm trying to. So remember this result, right? So there was this argument that, so if you want to control the packing number of a ball in, so this is, let's say, the same unit ball, that would be like 1 over epsilon to the d volume of d divided the volume of d phi. So the argument was that basically compare the ratios. So this is so the volume of the bigger ball, this is like n times the volume of the smaller one. So you divide. So this is also epsilon to the d times the volume. So you divide, you get n should be bigger than basically. So these two would be the same. So let's say I want to do this for so let's say, I mean, intuitively, if I do, is this sort of clear roughly? So that you divide the volume of the bigger ball by the volume of the smaller balls. And that would give you, so for example, if I want to do like epsilon equal 1/2, right? So I get 2 to the d. So the number of balls of radius, or the packing number in yeah, one like the half. Okay, so there is like a 1/2 packing of E2 in L2 of size bigger than 1 over 1/2 to the d, right? So V2 to the d. Right. So let's say if I do multiply everything by 4, this would be 2 packing. So let's say 4V2 with the same thing, right? So if you rescale everything by 4, you would get, so roughly the radius of the bigger ball divided by the smaller ball to the d is how many you need. Okay, so the relative radii to the power d. Okay, so think a little bit about this. So let's get back here. So I wanna find the 2 packing of for d2. So it's like the radius of this divided by the radius at the n. So I get 2 to the n. So there is this much. So exponentially n. The next thing that you have to do is to calculate the KL divergence. Okay, so the KL divergence is, shall we calculate the KL divergence? Just for you to see maybe. So so P theta is basically normal theta sigma squared I, right? How do we calculate the KL divergence? So P theta prime would be it's like integral to d P theta prime would be, let's say they have densities, right, with respect to the Lebesgue measure. So what is the KL divergence if you have densities? P theta of x log P theta of x divided by P theta prime of x dx, right? P theta of x is, what is it? 2 pi n over 2 sigma to the n, let's say e to the negative I actually have y here, so let's do y. So y minus theta squared over 2, or 2 sigma squared, right? So we can write this as expectation basically under theta of log p theta y, p theta prime y, where y is distributed like p theta. So what is this ratio? P theta y divided by p theta prime y. If I take the log, so this part goes away, right? Sorry. I would get y minus theta prime squared, right? Minus divided by 2 sigma squared, right? You get, what do we get? Expand, what should we get? Get y, y squares cancel out, yeah, so you'd get theta prime negative 2 this plus theta prime squared minus say plus 2 theta y minus theta squared, right? So you say this is capital Y. If you haven't done any, don't make any mistakes here. Then when I take the expectation, what would happen if I take the expectation? Yeah, the expectation passes through. And then what happens? Right. Okay. So everything is linear. So what do we get is 2, 1, 2 sigma squared, negative 2 theta prime and theta plus theta prime squared plus 2 theta minus theta squared. Did I get what I want? Right, okay. So this is going to be theta squared, right? And this is just what we hoped, right? Okay, so that's reasonable. So the KL divergence basically measures how close that the means are in the L2 norm divided by sigma squared. And then there's a factor of 2. It's a very reasonable. So this deviation divided by sigma squared is a measure of signal to noise ratio, right? So that's natural. So that's the KL divergence. Okay. So you can see if my parameters are close relative to sigma squared, then I'm going to have trouble. So with this construction, the KL diameter, because we're in 4B2, the diameter of this is 8, right? So you get 8 squared and then 1/2 sigma squared. So that d that I defined, which is the KL is like the distance squared. So you get this, right? And then you plug in into the Fano's inequality. There is like the delta squared here. Delta here is 2, so you get that minus, this is that d. So this is 2, d is what we have. And then log m is like this. Okay, so you plug in this and that, and then this is a bound. So this is, this gives you a lower bound. So if n is large, this is, you can ignore this, let's say. So this gives you 1/n here. And then 1/sigma, like 32/sigma squared and log n. So this is going to go to 0 as n goes to infinity. So for sufficiently large n, this is going to be bounded by a constant, so you get a constant lower bound. Okay, this gives you a lower bound, but this is not the optimal lower bound. Okay, you can do much better than this, but this is like one approach, and it gives you a bound. It shows that at least this cannot go to 0. Okay, so you shouldn't expect to be able to make this to go to 0. So as the sample size grows, this is not gonna converge to 0. There's no way to consistently estimate data. Questions? So what else we can do? We can do a little bit better, actually a lot better. This is sometimes referred to as a local packing. So instead of packing the like 4B2 is in there, but it also can fit like something like this would be in there. 4 delta root n B2. Okay, that's there in Rn. So let's work with this and then decide delta at the end. So pick this. This is a subset of Rn. Pick a 2 delta root n. So this is similar to what we did, right? So in terms of the cardinality of the packing, I just have to divide the radius of this by the radius here. Still gives me 2 to the n. Okay, so the cardinality is the same. Now the KL divergence, you can see, is going to be different a little bit. So for delta, this is the diameter in the L2 would be twice this, so I get that. You square everything, you get something like that. Okay, now I can plug in into the Fano's inequality. I have 2 delta packing, so the delta in these arguments, remember there's like a 2 delta. This is the delta. So I have 2. This is my delta from those arguments. So this goes here, square. Okay. And then I have this goes there. And then log m goes here. Okay. Now you can see I can choose delta. For example, if I take delta to be delta squared to be sigma squared over 64, right? Sigma squared cancels out. This is going to be like n over 2, right? Log 2 n over n log 2. And then there's going to be sigma squared n over 64 here. So you can do some sort of calculations. For example, let's say fn is bigger than 8. Do the calculus. So this is going to be like 1 minus this, like 1 over 2 log 2 would be 1.2 minus 1 over n. N bigger than 8. This whole thing is going to be bigger than 0.04, let's say, if I haven't done any mistakes. So this is going to be basically bigger than, for n bigger than or equal to 8, this is going to be bigger than sigma squared times n times like 1 over 64 times 0.04, which is this number. Okay, so there is this number positive, right, times sigma squared n. So compared with what we had here, which was like a constant, this is much better, and it captures the difficulty of the problem. So what it's saying is that for sufficient large n, it's n bigger than 8, I can't do better than sigma squared times n. Okay, this grows with n, and this is optimal. So there is an estimator that achieves this bound. What is that estimator? The MLE, what is the MLE in this model? Not the average, just y, right? Y itself, right? So the MLE would be theta hat MLE would be just y. So expectation theta hat minus theta squared would be expectation of y minus theta, right? Y is normal theta and sigma squared I. What would this be? This would be basically the expectation of a random variable. So y minus theta is normal, which means 0. where n is sigma squared I n, right? What is the expectation squared here? Yeah, so that would be sigma squared n. Sorry? Yes, it is. But the point of this is that this is saying that no estimator, including James Stein, can do better than this. The MLE does like that. So the risk is sandwiched between constant sigma squared n times constant sigma. So the difference asymptotically is in the constants, okay? You can dominate this, you can do strictly better than this, but the point of the minimax lower bounds is that asymptotically you can do, so basically what you're paying, the price is like sigma squared per coordinate, and they're n coordinates, okay? If you divide by 1 over n, that would give you that the error is like sigma squared per coordinate. That's not improvable. And this gives you a formal proof that in the normal means model without any extra assumptions, that's how much you pay. Okay. So James Stein is good, but just improves the constants. So one extension, now suppose I have a linear model, right? X beta. So this is x beta now instead of a theta sigma squared I. Beta is in Rn, sorry, beta is in Rd. X is in n times, is an n times d matrix. You're going to assume that the rank of x is R. For example, if d is less than n, usually much less than n, usually you assume that the rank is d actually, the classical setting. But let's say it'll be a little more general. This is R, which is less than the minimum of n and d. So one question is that what is the lower minimax lower bound on the prediction error? So you have x beta hat minus x beta. If you recall, this quantity is like the empirical L2 norm for the function that's estimating. So this is like empirical norm, if you recall. F beta hat minus f beta in the empirical norm, where f beta is just beta inner product with x. So this is just the expectation 1 over n summation f beta hat xi minus f beta xi. So it's measuring how well you're doing in terms of the value of this function, which is the prediction for your response. Okay, so this is equivalent to the normal means model that we just saw. So I can write it like that, where theta is in this theta, capital theta. Okay, so now the only difference with the previous case was this was Rn. Now this set is the image of x, which is basically this is going to be an R-dimensional subspace of Rn, right? Because the rank of x is R. There are at most R linear independent columns. So this is the collection of all possible linear combinations. So this spans a subspace of dimension most R. Okay, so now we can go through a similar argument. So I'm gonna just patch this argument a little bit. So 2 delta root n packing, we had 2 delta root packing of this guy. Now I'm gonna intersect this with theta. Okay, so I want a 2 delta root n packing this ball intersected with theta. By volume ratio argument, this is going to be, so this is a ball, because this is a linear subspace. This is still a ball, but in an R-dimensional space. And so you're basically dividing. When you try to pack things, you can just restrict all the balls to the subspace. It's as if you're working in R-dimensional space. So if you think a little bit about this, you'd get the ratios of the radii to the dimension. So it used to be n, now it's r. Okay, because I don't have n degrees of freedom. I have r degrees of freedom. It doesn't matter which is this is a general subspace as long as we as long as it's a proper subspace, everything works as if you're in Rn. Sorry, R to the R. So that's this. So the key is that I can't pack as much. No, I have to like pack into the subspace, but the dimension is not big enough. So I'm gonna have this much. This side is the same. This is exactly the same because the diameter is still gonna be at most this. So this is not changed this relative to this. It's exactly the same diameter here. So once you write down the Fano argument together with the reduction that we had, so you get delta root n here. That's this. Here is exactly the same now. This is r log 2. So now what I can do here is I want to balance the two. So if I take delta squared to be r sigma squared divided by 64n, you can see that this is going to be r over 2. This is going to be r log 2. And then if it's r bigger than 8, everything goes through with r replaced with n replaced with r, so you get sigma squared r. Okay, and then there's an n here missing. Sigma squared r n. There's an n here. Okay. This is r, this is n. So the bound that you get is, oh sorry, no. This is sigma squared r. That's because the n cancels out with this. If I look at the, so this is basically x beta hat minus x beta. So this is correct. If I divide by 1 over n, I get the bound on the prediction error. So I get sigma squared r divided by n. Okay, so this recovers the previous result if r is equal to n, but it's much better if r is a constant. So if you're doing like regression in finite dimensions like d, and n is bigger than d, so this is at most d, and if x is actually really rank d, then you get sigma squared d over n, which is going to 0. And you can argue that the OLS achieves this. If the rank is bigger than n, basically, this is just going to be Rn. You're back to the no constraint. So if the rank is bigger than n, there's no, this is just going to be sigma squared. Not bigger than, so like equal to n. Yeah. Yeah, so what I'm saying is that this is achieved by OLS if rank is less than or equal to n. If d is bigger than n, and the rank is at most n, basically the OLS, you can just disregard OLS, basically. You don't need to consider OLS for d. Yeah, so it doesn't matter as long as you do. The thing is, no matter what estimator you use, let's say once d is bigger, so let's say d is much larger than n, right? What happens is that this is going to be, so let's say d is bigger than n and the rank r is actually n. Okay, then this will be just Rn. So you're back to the original normal means model, so you can't do whatever estimator you use, ridge or whatever fancy estimator you use, the bound would be sigma squared. Okay, so you can't. That just shows that there's no hope in high dimensions without extra assumptions. No, if you don't impose any other constraints, this is basically the normal means model. Once the d goes, as long as the prediction error, so you can see easily that as long as you care about the prediction error, once d is bigger than n, without any constraints, if it could be D is bigger than N, but the rank is still like smaller than N. But let's say D is bigger than N and the rank is the maximum. This argument shows that this is just the usual normal means model. Nothing you can do, just output Y. Y is doing as good. Right, there's no. Yes, exactly. So that's the idea of like doing sparsely. That's what I want to do next. But just this argument shows you that you can't do basically anything without extra conditions, right? It just shows that there is another interesting case is where R equal to 1. So suppose you have the classical, the usual case that you usually have, this is equal to theta plus noise, right? There's like one single theta. You have a sample of size 1, sorry, sample size of size n. This is like the normal means model where you have theta times indicate like the vector of all ones. Normal theta 1n sigma squared I. So that would be your x basically. Let's call this beta. So you have beta, single beta. So this is like x beta where x just has like n by 1, just a single vector. Right, this is x. And so the rank would be 1, so this is going to be 1, v1, so sigma squared over n, that's the parametric rate. And it's achieved by the average, for example. So it also shows that in the Gaussian case, you can't improve. In this case, the best thing that you can do is like do the OLS, which is just the average. You take the average of yi's, this is showing that the average. So if you think about this, this is going to be 1 n times beta hat minus 1 n times beta. The 1 n's cancel, so this 1 over n goes away. So you get this norm would be n times beta hat minus beta. So this would be just saying expectation of beta hat. This is univariate now. This is bigger than after constant sigma squared over n. Right, so this shows that the parametric in the parametric case, like the average is minimax optimal. Okay. Good. Any questions? So now the difficult part. Let's not worry about this. Let's see how much time we have. We may have to like, this is the case where you impose more conditions now. Suppose you have a linear model and x beta sigma squared I n, x is n times d. We're going to assume that beta belongs to this set. This is slightly less natural. So what you would have done is look at beta belonging to this. Okay, that would be the equivalent to the linear model because this also restricts the size of betas. Whereas in this model, we just assumed that beta is anything in RD. There was no restriction, so this was a solid space. Here it's a little bit tricky. If you're interested, you can try to work out what happens if I remove this. I would be interested in seeing what you come up with. But let's say we work with this. This still captures the complexity. At least this provides a lower bound on the case where you remove this, right? Because this adds another restriction to the set of betas. So this provides a lower bound on the minimax risk where this doesn't appear. Okay. But okay, so let's put this there. So then you can still ask what is, again, minimax lower bound of the prediction error. This is the equivalent of obtaining the minimax lower bound in the normal means model, where you have x beta, beta now belongs to this instead of, yeah. Yes, x is fixed, yes. So x is the same design as before, it's a constant fixed design. But hopefully s is much less than d. So this is slightly different, the technology here. And so you have to first find a packing of this. And this is the claim that if you have time, I'm going to come back and together we'll think about it. This is the hard part. So there exists a 1/2 packing of this set. That has this cardinality, log cardinality. So I can find a packing of this 1/2 packing of this that has cardinality like that. Let's come back to this. We'll have time. Otherwise, you have to think about it. Let's assume that this holds. Then, if I assume that S, for example, is less than d/2, which is reasonable, it's a reasonable assumption. Otherwise, there's no sparsity. At least half of the coordinates you need to be 0. Then this is going to be lower bounded by d/2, right? Is it lower bounded or upper bounded? Yeah, this is going to be bigger than d/2. And then up to constant, I can say S log E d/S. E is because upper bounds usually like have E in them. But this is like saying this is up to constants like S log d/2/S, which is further up to constants. This is up to constants equivalent to S log E d/S, because the constants will just add something times S, which is dominated by the other term. So in any case, so the whole point is that there is this. So roughly, what it's saying is that there is like a packing I can find that is like E d/S to the CS for some constant C. Let's call it C1. So this is the tricky part. So if you can find such a packing in L2, then if I multiply every one of these by 2 delta, so actually if I multiply every one by 4 delta, that would give me a 2 delta packing. And the pairwise distances would be at most 4 delta. Is that true? Delta packing. Is this true or not? So if I have a packing of this, then it means that beta I minus beta J, this is, they're pairwise bounded by 1/2. If I multiply by 4 delta, right? They would definitely be bounded by, is this going to be 8 delta? So beta i's are in the norm is less than 1, because in this third in this. So if I multiply by 2 delta, yeah, I'm not sure. Maybe 8. Either 4 or 8. This, I think your book says 4, but at least this would work. Right? If I multiply both sides of this by 4 delta, they're going to be where? That's okay. So that's the thing. So I want to. So these are in the L2 wall, right? So what I have is like beta I minus beta J is also bounded by 2, right? So now if I multiply everything by 4 delta, right? So 4 delta beta I from 1 to n, right, would be, so I get 4 delta beta I minus 4 delta beta J, bigger than 2 delta, right? And this would also be 4 delta beta I minus 4 delta beta J would be less than 8 delta, right? So it seems like at least with 8 holds, I think there are some probably typos in the argument in the book here. Not sure. See. So later, let's say delta is going to be small. So assume that, let's say for delta, we have to assume that this is less than or equal to 1. So still, this is going to be inside this. Okay, because these are going to be S sparse by construction. Multiplying this, there's the remain in that. But now I have some sort of a local packing, which means that I'm packing inside the ball of radius, or at least the radius for delta, and I have this. So this is the idea of the local. So this delta we can choose later. So I have that, and then also let's define this constant, the operator norm of x sub t. This is the t that you take the so you recall this notation. I have x. This is high dimensional. This is t. So x sub t is just subset of, this is n by d. So this is the subset of columns of, or x restricted to the columns indexed by t. And so this is the operator norm x t divided by root n. And then I take the maximum over all subsets of size 2s. Okay, so that's gamma 2s. We note that this guy is going to be, so x beta I minus x beta j. It can be written as root n, right? X beta I minus beta j divided by root n. And beta I minus beta j is 2s sparse, right? Because each one is a sparse. So they fall within this sort of framework. And so this is going to be root n bounded by x. So this is, okay, let's do this. This is going to be bounded by x t over root n for some t, which is the support of these two. Right, this is the union of the support. T is the union of the support. And so this is going to be bounded by root n gamma 2s. And this is, we concluded that this is like 8 delta. Okay, so that's the bound that we have here. So if I put 8 here, we have this bound, root n gamma 2s 8 delta. And then if you recall, the diameter in the KL is just theta minus theta prime, or x beta minus x beta prime squared divided by 2 sigma squared. So I get this squared. This guy is squared divided by 2 sigma squared. So I get gamma 2. There should be 8 delta root n squared divided by 2 sigma squared. That's the diameter in the KL. That's the normal means calculations. And so you now plug in, so you have a 2 delta packing. So you get a delta squared here. And then this is what I've plugged in here. So from this, yes, we need to upgrade this. So 8 squared would be 64. So I get 32 here. So this would be 32 delta squared n gamma 2s squared divided by 2 goes away, yeah, sigma squared. So that's what I'm putting here, right? I have this thing, which is stated without proof there. And then you can see if I choose delta squared to be, I just want this to be roughly a constant multiple of this. Okay, so you want basically gamma 2s squared delta squared n over sigma squared to be like a constant c prime times c1 s log ED over S. And C prime, if you make it, say 32. So if you make C prime small enough, you can make that go away. So in the end, what we get is delta squared is some C, which you can choose, sigma squared over N, and then 1 over gamma 2S squared, and then S log ED over S. I think I'm putting N here, sigma squared. So that's the whole thing. Okay. So that's the rate. So that's the rate. I mean, this operation allows you to make this a constant small enough so that ignoring this, you can also like make this go. So assuming that this is large enough, this is going to dominate this. So let's say S goes to infinity, S is big enough. We assume that S is bigger than 10, like let's say we cancel this out, and then this part, make it a constant. And then this whole thing would be bigger than 1, and so that's the rate. And you can see it just this sort of matches. This is the let's say if we ignore this, whether this is optimal, it may be optimal, but sigma squared S log ED over S over divided by N, that's the bounds that you get from your homework problems or from other considerations. This is this is showing that you can do better than this. And let's say the L0 penalized regression or constraint L0. So if you solve the do the maximum likelihood, it's just minimizing y minus x beta squared, let's say subject to this constant condition. If you do this, you can show a matching upper bound. I believe you do it in your homework problem 4 problem. And so this shows that this is the optimal rate. So roughly speaking, it's like sigma squared S over N. This is similar to this, right? Sigma squared R over N, right? Because the dimension is roughly S, but the price that you pay here is this log, extra log, right? This is the price that you pay because you don't know the subset. So the tricky part, which I skipped, and I would like to let you do it, is this. This is a homework problem in your whole, like in your book. The details are not enough to be able to figure out, but I'll let you, like as a bonus problem, if you can solve, the first person that solves this and send me a proof on campus wire gets a bonus. The idea is to use the so-called Warsham of Gilbert. This is a lemma. This is the version that I stated from this book, Introduction to Non-Parametric Estimation. It's somewhere also in your book, HDS. I couldn't find. It's a very useful book sorry, it's a useful lemma. This is also a useful book, but this is a useful lemma. And the proof is interesting, so you could look at the proof of this uses the Hoffman inequality. So this says that if you have the hypercube, let's say binary cube, you can find, let's say m+1 points here that are, this is the Hamming distance. So the cube, the binary cube equipped with the Hamming distance is a metric space. Hamming distance is, you know, Hamming distance, right? You have 2 sequences. These are 6 binary sequences. 2 binary sequences. The Hamming distance is the number of positions that they differ, right? So this is the natural metric here. So this is saying that you can find that basically d over 8 packing of cardinality m+1, where m is bigger than 2d over 8. So the advantage of this version is that you can also include 0, and the way it's proved, you get a construction, you can sort of see where different things are, but including the origin and m other things, you can pack as many. So this is saying that there are exponentially many, exponentially in dimension many points that you can pack on the hypercube that are like within a fraction of the dimension of the cube in terms of the packing. So the idea is to use this together with the other thing that you know about low-dimensional. So you have to sort of use the Warshamov-Gilbert to control the differences of the hyperplanes. So like, this is a union of subspaces, but you want to also two different subspaces when you can pack within each subspace, but then you want the packings within different subspaces to also be separate from each other. And somehow you have to use hopefully a version of this together with the packing within subspaces. Something like this should be. So this I'll leave you as leave as an exercise. Okay. Let me know if you manage to prove this with these constants or with some other constants. So this like a bonus exercise. That's the key thing. And the log here is the one that matters. So without the log, you get this, which is not very interesting. You could just do this. You can get this bound easily from the previous bound, right? Because you could just pick one of the subspaces here. So this is a union subspace. Pick one of the subspaces, just apply the previous result. So you get sigma squared S over N easily from the previous result. The key is that I want to also get this extra juice here. And that requires you to sort of consider packings over all possible subspaces. Okay, so in the remaining time, I'm going to quickly, yeah, we don't have enough time to go through this, but let me mention there is this other upper bound. This is known as Yang and Barron because it appeared in a paper by Yang and Barron. There's this nice upper bound on the entropy, which you can do by, if you can manage to perform an epsilon cover of the family of probability distributions that you have. So you have like P, remember that was P theta 1 up to P theta M. So if I can cover in the square root, so as I mentioned, this looks like Euclidean distance. So it would be like, remember in this context, so the square root, the P theta prime, this would be proportional to the distance divided by sigma, like root 2 sigma. So packing in this, packing the probability space in this metric is like packing the original parameter in the scaled L2 norm. So if I can pack in the epsilon, like if I have an epsilon packing, sorry, epsilon covering of P in the KL divergence, that will be the epsilon covering number. Then I have this upper bound on the what? On the mutual information. So then I can use this together with so you would have something like, this is the infimum. So if you pick any epsilon, you get an upper bound, right? So so you would get delta squared, that's from the packing that we had. So you epsilon squared plus log NKL epsilon P plus log 2 divided by log, this is M delta. Okay, so the idea is what would happen is that you pick epsilon such that basically epsilon is roughly equal to log NK L epsilon, and then this side would be roughly equal to like a constant times epsilon squared, and then you try to match this. You find a delta such that log M delta is roughly, let's call this epsilon n because it usually depends on n. So choose a delta such that it's like that, and that delta n would just then be the rate. So let me maybe very quickly try to do this. I'm going to skip the proof. The proof is simple. So the context of this is what we can use to analyze this non-parametric regression model. It's just, again, as you recall, it's a subset of, it's just another version of the normal means model, but we can use the entropy of function classes. So let's say I'm going to use the L2 norm as the metric, so that row metric that we had. So I want infimum over f hat, supremum f in f, expectation, the true L2 norm. So you assume that xi's are coming from some probability measure. And what we want to do is something like that. Okay, so we want to show this. And if you have some sort of a, let's say, entropy number of the class of function, your function class, let's say delta f, and the L2 norm is like 1 over delta to the 1 over alpha. So for example, for the Lipschitz class, this is going to be 1. We have shown it in the infinity norm, but over a bounded set, it would be the same. So if you have something like that, then what you would do is that diameter, there's some sort of averaging out going on, but you can show that once you average out over this, the KL divergence in this model would be something similar. So it would be f, it's like the maximum, max over I, or j not equal to j prime, j minus fj prime. Let's see if we can do this. That would be this, and then okay, I think probably I can't. So in the KL, because the KL sort of, there's this extra piece here, this would be like combined with this, because it's related to the L2 norm up to this factor. You can show that this is like root n sigma epsilon to the 1 over alpha. And then you set it equal to epsilon squared, you solve, you get epsilon squared is n over sigma squared, 1 over 2 alpha plus 1. And then you have also log m delta. This is of the same order. It's like 1 over delta over 1. This, you set it equal to roughly equal to epsilon squared, which is n sigma squared, 1 over 2 alpha plus 1. And then this gives you delta, which is hopefully something like that. This was very fast, but or delta squared, which is sigma squared over n2 alpha. Yeah, I wish we could do it like a bit better. But the point is that the KL divergence here is up to this constant is proportional to the L2 norm. So the packing and the covering number have the same, both the packing and the covering number of this form. So you can basically, up to this, the KL packing, the K covering is like that, and then the packing is like this. You solve for this, you set it equal to that. So the reason why we solve for this is because of this equation. And then once you have the epsilon, you solve for this, you get the delta. And that would give you the delta. This is going to be the minimax lower rate. And for example, for alpha equal 1, this is going to be what it would be. So the minimax lower bound is sigma squared over n to the 2 over 3, which is what we get for the Lipschitz class. So this argument shows that because for the Lipschitz class, this is going to hold with alpha equal to 1. This shows that for the Lipschitz class, you can't do better than this. So that sort of closes the gap. So this was fast, sorry, because we ran out of time. But if you're interested, look at the proof is simple, the proof of this, but the technology is very interesting because once we can control the packing, the packing number, and then the covering number in the square root KL, in some cases, they're basically the same, of the same order, then then basically you can do this sort of calculation, find the epsilon, then find the delta that matches this, and then your delta would be the minimax rate. Okay. Okay, thank you guys. Hope you learned something in this course. Next time we come back and you guys continue, and let me know if you have any